to the dynamics tutorials. With this problem, we've got a roller coaster. It's at an initial height of h at A. It goes down to the ground level here at B, and then it goes through a loop. We're investigating the top of the loop here at C. The loop is circular and has a radius of 10 meters. So we want to find the minimum height h at A so that the roller coaster won't leave the track at C, and then we'll use that to go back and back calculate the velocity or speed rather at B. So here's our free body diagram at C. In the limit of the roller coaster about to leave the track, the normal force of the track on the roller coaster will be 0. So this normal force here is 0. So we've got our tangential direction going in the direction of the path. So going in this direction at C. We've got the normal direction coming down here towards the center of our 10 meters radius. And then we have the weight acting on the object. So the weight is the only force that's on the object. So we do our sum of forces in the normal direction is equal to mass times the acceleration in the normal direction. This gives us our weight, 1,000 kilograms times 9.81 meters per second squared is equal to the mass times the velocity at c squared divided by the radius of curvature. Remember that for the acceleration in the normal direction, it's always v squared divided by the radius of curvature. This gives us this equation, and we can solve for Vc, and we get 9.90 meters per second. Then you can solve it either with work and energy or with conservation of energy. Let's take a quick look at work and energy, and then I'll explain conservation of energy. With work and energy, you have your initial kinetic energy T1 plus the sum of all the work done from going from the position 1 to position 2, and that's equal to your final kinetic energy. This is just a particle. We don't have any information about the size, and so it's just going to be 1/2 mv squared for our final kinetic energy, and the only force that we have acting on this that's doing work is the weight, so we have our minus w times delta y. If you wanted to use conservation of energy, you could. You'd have that your initial kinetic energy plus your initial potential energy is equal to your final kinetic energy plus your final potential energy, and you'd wind up with the same equation. You'd get 0 here because it's starting from rest, plus the weight times the y position at A is equal to 1/2 mv squared for your kinetic energy plus the weight times the y position at C. So bringing this over, you'd wind up with the same weight times the difference of the two y positions. Going back to work and energy now and applying all the numbers, our weight is our mass, 1,000 times acceleration due to gravity. We're going from a height here, a final height of 20 meters, so it's going to be our final height minus our initial height of h, so there's our 20 meters minus h, and then here's our kinetic energy, 1/2 our mass, 1,000 times our velocity at point c squared. We can cross out the 1,000s because they're, just factor them out. It gives us this equation here, and then solving for h, we get that h is 25 meters. Remember that since this is a radius of 10 meters, that's why we're using this height of 20 meters because we need the full diameter. Then to go back and calculate the velocity at B, we can use work and energy again. So we can say that the kinetic energy plus the work done gives you the final kinetic energy. And so our work is just, again, the work that gravity does due to the weight. So we've got our weight times our change in our y position. We're going to end up at B, so we've got 0 for our y value minus our initial y value of 25. And then on this side, we have our 1/2 our mass times our velocity at b squared. Solving this gives us a velocity at b of 22.1 meters per second. Thanks for watching.